Okay, our next speaker is Dr. Bob Schafrik, who is General Manager of the Materials and Process Engineering Department at GE Aviation. So, welcome, Bob.
Good, thanks, Joe. Okay, so what I'm going to talk about is from our perspective in my business, aviation, where we make the aircraft engines. You know, what are our objectives for ICME? And then I'll summarize some of our current activities and then leverage from that what our vision of the future would be. And that leads to a slide on challenges and then one slide on a wrap-up for a takeaway. Okay, so I think it's important to point out that you know, I'm looking at it from an industrial point of view. And at the end, I'll come back to that point because I think whatever we do with an ecosystem, it needs to satisfy objectives not only from industry standpoint, but from academia and government labs, et cetera. Okay, but anyway, one of our key objectives is to capture and apply knowledge. And like many of you all in your businesses or your departments, you have a lot of people with a huge amount of experience that are retiring, and they have a lot of things in their head. And you know, it's been my dream, why can't we capture that in like some kind of a model, you know, that's validated? And we've had some degree of success the last few years of being able to do that. Importantly, from a business standpoint, it's also important for us, for me in particular, to keep my job to show, you know, we improve our productivity. And by that, we're talking about shortening our development time, but do it in a smart way so you not only don't increase the development risk, but we do just the opposite and decrease the development risk. And it turns out from our experience, which I'll give a couple of examples, it actually works that way. If you have an accelerated program, you lay it out the right way, risk is actually less because the requirements don't change. You know, you don't have a moving target to shoot for. And lastly, the name of the game is to design some better components. And it enables us to have much better confidence in showing our business customers that we're able to improve our products with these new materials, even before we have all the data for the new materials. So that's the huge paradigm change here. Be able to forecast ahead of time what you're going to do, and then you do it, and you do it at low risk, and actually it works. Okay, so here's a slide I leveraged from Deb Whitus, you know, sitting in the audience there, and this we did this as part of the DARPA AIM program. You know, when we were thinking about what is our end goal. Well, we want to be more like the people in the design world, where we can do analyses in hours to weeks, instead of weeks to months and actually to years. You know, is what it takes us in some cases. So the fact is we didn't have the tools to do that effectively. Now we could take educated guesses, but at the end of the day, our chief engineers and the aviation authorities, they don't want our guesses. You know, they want analysis as well as the data. So that was our challenge to put some tools in place. And here's another chart I leveraged from Deb, which it's kind of a mapping of our business processes from a material standpoint. And up there in the upper left-hand corner, you know, is what you tend to focus on I'm thinking of material models and stuff, is developing new materials, either metallic or non-metallic. But you see, if you look at the scale, that is a high level of effort, but it doesn't happen too often. Same with developing new processes. But there are other things like doing analysis of design changes to existing parts or making some change to an existing process, which happens quite frequently. And if you integrate all these different activities, it turns out these other activities are more than 50% of our workload compared to doing the new thing. So the point is, whatever tools we develop, we want to be useful, not only to develop new materials, but also to help us with these other problems. Okay, so let me just summarize just what our current activities are. Well, first of all, and I must say, at the instigation of Steve Wax at the beginning of the DARPA AIM program, we put together, we integrated well with the design teams. And maybe 10 years ago that was a shotgun marriage. Now it's really works really well, and to the extent our people are even co-located with our design teams. We also, have many models which for processing and physics-based models to predict properties. And it won't be that long until, this is in the 3 digits here in terms of the number of models, which is good news, but it's bad news too in the management sense of configuration management, if you will. But I'll show an example how this actually helped us a lot in our scale-up time for developing our materials. And one example, and some of our younger folks now, they don't appreciate, it used to take us 3 iterations at least to get the shape of a complex forging die right. Well, now we do it in one shot, and no one thinks it shouldn't be that way. And they're right, it shouldn't be that way. But within a reasonably short time, that shows how far we've come. Also, we have a huge amount of data, and it's heterogeneous data. And we're in the final throes of digitizing all of our past data, and honestly, it's in the terabytes. And one of the things you learn, it's not too hard to store data. It's a lot more challenging to be able to find that data later and put it in a useful form for whatever analysis that you want to do with that data. Okay, now we're rapidly expanding our applications for our new materials across all the product lines, and that's really driven by the competitive environment that we're currently in. Fortunately, what we're able to do with our modeling tools, has allowed us to do that in a reasonable way. And importantly here, and I'll show 2 examples of this, we have been able to accelerate our development of some key materials, and that has caused the leadership within our company to have expectation that we could do this all the time. And I say, boy, I created a monster here in a way, but the fact is, that is the wave of the future, and that is the right thing to do. And that's really what the second half of my talk is going to talk about. What is it that we need to do to allow us to have faster effort on developing things as a matter of course. And associated with that, one of the things we're currently doing now is being able to estimate what properties we'll have for these new materials. And of course, we're not talking about average data here. This is the -3 sigma data that our designers use. And that's not just necessarily an offset curve, because it has to take into account our assessment of defects in the material that arise from processing, chemistry variations, and that sort of thing. Okay, just real quickly, this is a chart I put together a few years ago, and actually did a survey from aerospace and non-aerospace, briefed it a few times, and it's pretty much held to be reasonable. Is if you modify an existing material for a part that's not critical, that was a minimum of 2 to 3 years. If it was for a critical application, you could pretty much double that time. If in fact it was a new material, or say a major chemistry change within a material system like nickel superalloys that we already have experience, but it's a significant chemistry change, well, it doubles again. And then if it's a new class of materials like intermetallic or ceramic matrix composite, it doubles again. Of course, I was generous to say up to 20 years, but it's longer than that in many cases. So that's what the past history has been. Okay, so here are 2 programs that we've done within the last few years that managed to cut that time in half, or a little bit more than in half. First is the work on developing a single crystal alloy for turbine blades with low rhenium or no rhenium. Now, it was based on Rene N5, which had 3% rhenium. And about 4 years ago, we determined that if we did nothing, just the GE use of rhenium would exceed the world's capacity, that very rare alloy. And so we were given the charge to do something about it. So we did a lot of work in recovery and recycling. But beyond that, we were asked to look at changing the chemistry of these alloys, of N5, which already was pretty complicated. And it turned out that kind of parallel to the work we were doing on DISC in the DARPA AIM program, we had thought that someday they're going to ask us to do a new turbine blade. So on our own, we put in a bunch of tools to get ready for that day. And when the day came, they worked extremely well. So we were able to do that program instead of the 6 years. We did it in 2 years. And I'll show you that 2 years means from the start of the program until full engine qualification by the FAA. So that includes engine test, engine flight test, in multiple engines. So it was something you would think would be impossible to do, in the past. And the predictions from the model helped guide our technical strategy for sure, but the other key is having very smart people to know how to interpret their models and make some judgment. And by the way, we never rely on just one model to make a decision. We use multiple models, look at it different ways. So it takes, a lot of expert judgment to do this sort of thing. And then recently, we've done a new cast and wrought disc alloy, which was going to be called R65, and it's based on a powder disc alloy. But again, it was a chemistry change that that wasn't trivial, and this was done as a cost reduction. And normally that would be a 10 to 12 year kind of program. And we did it in 4 years to full scale up in multiple engine applications. And models were really key to help us predict the strength and stability of those chemistry changes. And importantly, the processing route, which could be pretty tricky, for these high-strength superalloys. In fact, I'll have a couple of charts, but one of the significant things here is we didn't do any subscale heats on this. We went immediately to full scale. So that first experiment cost about $1 million, to do. So it was, they told me to take a big swing, and I did, and luckily, it worked. Okay, for the low rhenium alloy, and there's been papers by Doug Konitzer and Paul Fink and several other people from GE kind of talk more about the details. So all I have here is the high-level charts, but you can see we did 6 months of a design of experiments, and we quickly saw that our estimates of what the results would be matched the data that we were getting. And so that got us kind of excited, and I was able to go to my leadership and convince our CEO that we were ready for a decision to scale up the chemistry for those two alloys after 6 months. And then the key thing was he allocated funding, for the rest of the program. So I didn't have to keep fighting the funding battle, which a lot of times slows you down too on these development programs. And once we made the scale-up decision, we went immediately to full-scale heats. We were able to dial in the castability so we could use existing tooling, which saved a tremendous amount of time. And we made a lot of single crystal airfoils. And from the time we made the scale-up decision until we put it in the production engines for test, was only 6 months. And then we got some flight testing as a result. So this date here is FAA qualification of the design change in the engine, and it was in multiple engines. It wasn't just one. On the cast and wrought disc alloy, typical, this kind of shows the 10 or 12-year way we've typically done things. And you can see the first half of the time it's 2 or 3 rounds of design of experiments at subscale. Then we go full scale, and then we have a lot of things we do in parallel. And almost always when you go from subscale to full scale, you learn things that you didn't anticipate. And so there's some rework loops in here, which cause the time to drag out. So we thought if we really were confident in the tools that we had built, in the way we did the analysis, let's eliminate all this subscale work and go immediately to full scale. And that's what we did. And so this shows taking this and collapsing that to a 4-year program. Now, actually, it's going to go to 4.5 years on some of our engines just because the engine tests, have been delayed a little bit in some cases. And so here's what we were able to do. We made 600,000 pounds of this alloy. We used 10 forgers, made 250 forgings of all different sizes. And when you add up all the testing we've done just on our side of testing, that's 1 million hours of testing. Now, we've never introduced a new disc alloy after even 12 years, with 1 million hours on different test frames around the world. It's fatigue testing, tensile testing, creep testing, or what have you. And it's also the first disc alloy that's gone into multiple engine applications at the same time. So it was a big bet that really has paid off, and thank goodness it did. Okay, so what have we learned on developing models? Well, first of all, you had the problem as to which models do you want to develop, because there's a large number of those. And so we say, well, what activities are we doing that could benefit the most from modeling tools? And then we look to see what's available in terms of capability and what's their limitations as far as we can determine. And then which existing models could maybe be improved, or be extended to go help us. And then we use this to do some prioritization. And then the options we consider, of course, are licensing, buying packaged software. Another option is development with others in a collaborative way. And one of the best examples is the Air Force program on metals affordability, which has helped us quite a bit. And that's where we work across the industry with our competitors and airframers and suppliers, in developing models. And then we have a major effort that we do ourselves internally. But the end state that we look at is we want a set of tools that's part of our engineering tool set. So it becomes a standard way that we do things. Okay, so that kind of leads then to the future. Well, one big aspect of the future is, well, we'll have hundreds. I could easily see we'll have hundreds of models, okay? But we want to be able to pick and choose the right models to link together, to run these simulations. And you want to be able to do that over different length scales, for example. So I think that's going to be a big deal. I alluded to this already, that my leadership expects that accelerating this material development is the norm. It's the new norm. So they don't even look at it as an acceleration anymore. They look at it as, this is the way you're going to do it. And with taking 2/3 of the time out, like I showed on those examples, that much more matches the NPI cycle. Now, I should have pointed out on those 2 examples of the low rhenium single crystal blade alloy, as well as the new cast and wrought disc alloy, which went into our existing engines as well as our new engines. We had the constraint of the existing engines and not changing the design of the part itself. And so that means the properties or whatever had to be better than or equal to what they currently were using then, for their application. So That's kind of a big deal. If you're designing a material just for a new engine, you have a lot more interaction with the design engineers on trade-offs that could be made. And that's another aspect of improvement that we make with our designers. Okay, and that leads to this integration with our design team, materials guys, and then the supply chain, because we have to scale. To do an accelerated program the way I showed, you have to be scaled up at the end of the development cycle. Okay, it's not like you develop it and then get it qualified and then scale it up. All that has to come together at the same time. Okay, we have a large amount of hybrid data now in digital form, and so that adds a challenge of the database that kind of Jim talked about. And another point for the future is our designers are intrigued with the idea of what we call location-specific properties, and that means instead of assuming, like on the turbine disk, that every part of the disk has the same properties, you could take advantage of the fact that it doesn't indeed have equal properties in all parts of the disk, and design it, for those localized properties. Well, that means you need a lot more material property data than what we have now. Okay. So this leads to the idea of, here's kind of a little plot that I did on the explosion of modeling tools that we have. See, you start with process models early on, structure models, and now heavily into property models. And that's an exponential curve, is what I believe. And so I leveraged this from the NRC report on ICME, which I liked. I only tweaked a few of the boxes. As you start with this knowledge base, you have these external interfaces, and then internal to the knowledge base, you have the heterogeneous database, you have the modeling tools, analysis method, ways to visualize the results of the simulation, and then, of course, cost model. And then we put that into the structure of like a software system. How would you implement that on something we call ICME net? And the key is you see these external links, which are determined by this governance model, which depending on who the users are, they have different type of permissions to see certain parts of the database or certain tools or whatever. So it's things that are agreed to up front, and then they would have full access to that. Now, what I showed, oops, I went too far. Let's see if I can back up. Well, in the interest of time, I won't back up. What the previous slide showed is for an advanced disk program, which I haven't talked about, but we're doing a brand new powder disk program besides the cast and wrought. There's a lot of interaction that's occurring, including with academia, but it's all done by hand, for the most part. This maps that into the framework of the ICME net to say, how could that data be, in the flow of information, be better handled with some kind of a structured software-based system. And in fact, we could do more with this kind of a system because there's a lot of information in the database that could be exploited more than what we're doing now. Okay, so what are some of the challenges? Well, one is not only doing the development, but we have to validate these models, and really, really important is do the maintenance of these models. And both the physics-based and the heuristic-based tools as we continue to get more data, more information. Also, I talked about this challenge of multi-scale modeling, multi-phenomena, how we really have to link these models together, and maybe sometimes in an iterative fashion. And importantly, establishing some sort of collaborative infrastructure, that we could use to do these things. Okay, then lastly, kind of the takeaway point is the turning back or doing something different than ICME, I view it's no longer an option because we did show what is possible to do with an accelerated program. And therefore, if success builds on itself, and because of some success, we've been able to get more internal funding to do development activities, and I'm glad there's external programs available, to do that as well. Now, the vision and objectives for what you want to do for ICME differs depending on where you fall in the spectrum here. And so whatever is done with the collaborative infrastructure needs to satisfy multiple needs. And lastly, this infrastructure, at the end of the day, it's going to be the glue that kind of holds everything together. And what I see now is with a lot of intense effort on the part of very expert people, we were able to craft things together in a way that worked well. But could I do it on a regular basis with folks with less experience? Clearly the answer is no. And I mean, I say that not only from the standpoint of my department, but the folks we work with in the supply chain and in academia. So we really do need to build this infrastructure in some way. So I think that's one of our big challenges as we look to the future. Okay, so thank you very much.